Okay, so there's one more lerping concept I'd like to talk about, and that is time-based lerping. So there are some problems with lerping so far. So lerp, as we use it, it relies on regular timing of frames. As we've used it, so the frames need to move at the same rate and at the predicted rate that you expected. So it relies on regular timing of frames. Okay, so what we do is we take t, and it goes from 0 to 1, but because we know how fast we're drawing, 30 frames a second or 60 frames a second or whatever, we've translated this into an even number of steps. Right? You go, okay, I want this to happen this fast, so do this over 200 steps. But what happens if we can't rely on that? What if the frame timing changes? What happens then? What happens to our lerp if we can't rely on that anymore? So there are two places, it's really common actually, that this will come up. What if the timing becomes irregular? Right? You're in the middle of a game and a virus scanner starts up. Okay, you could have a busy CPU. Right? Your virus scanner starts up or something else happens in the background. You also might have a lower frame rate than anticipated. Okay, you have a lower frame rate, maybe someone did a configuration change. Oops. Or maybe there's suddenly a busy scene you didn't predict in your game, and then suddenly it's going at 15% slower. In all of this, in our code so far, if the frame becomes irregular or it slows down, the whole animations will change speed with it. All our animations will change speed. Okay, and that's not good, right? Let's make an unhappy face. This is not good. We can't have the animation speed relying on the frame rate. Okay, we can't do that. So I'm going to demo this problem for you. So here's a program. This is the same program I've been building the whole while. It has different modes of easing in and out and all that stuff. So what I'm going to do, there's some new stuff in here I'll talk about a little bit later. But what I'm going to do is I'm going to run the program so you can see it. See it running, and there's nothing unexpected here. It's the same program we've had before. Linear, ease in, out. Looks quite nice and smooth. It goes great. Now, what I'm going to do is I'm going to add some funky code down here. I'm going to add a random delay to simulate a regular frame rate. And remember how fast it was going before. Now it's much slower because of all these delays I put in, but also the speed is irregular. So sometimes it goes slow, sometimes it goes fast. In fact, let's make it even a little more irregular. Let's make it so that usually it goes full speed, but then 25% of the time it slows down. There we go. So smooth, fast, slow down, smooth, fast. So it becomes irregular. If it's going to have delays, we're going to have jerky and clunkiness anyway, but the actual speed or the motion across the screen is quite irregular. It speeds up and slows down based on the frame rate because our whole lerping is based on expectations of one frame. I'll also show this example here where instead of setting our frame rate to 60, I'm going to have the frame rate set to 15. So I'm going to take the exact same program, no funny delays. It's running at 15 frames a second. So the whole animation slows down. So if your game drops from 60 to 40 frames a second, everything shouldn't be 20% or 50% slower, depending which way you look at it. It shouldn't be 20 frames slower. Everything should be maybe choppier or clunkier and less smooth, but the speed should be the same. So this is the problem with frame-based lerping. you have these inconsistencies. The speed changes as the frame rate ebbs and flows. So we need to learn how to fix that. So the solution is, instead of basing it on the number of frames that we've drawn, we should use time as our go-to reference. Solution. We use time, not frame count, to determine t. Okay, let's explain how that works. So you can imagine I have my linear interpolation from configuration A to configuration B, right? A is when t is 0, and B is when t is 1. You can also imagine you have a spot in the middle, have t equals 0.5. Now let's say you plan this out to take roughly 2 seconds, okay? Now previously we're like, okay, I'm at 60 frames per second, right? I'm at 60 frames a second, so this should be 120 frames. In the code I've given you previously, instead of that, I said, how many pixels a second should I use? And I used that with a consistent frame rate to come up with how many steps my leg of my animation should take. It's the same thing. Oh, good. I had a message pop up. I was making sure it's not on your screen too. So instead of basing it on these number of frames, we can say, well, let's just base it on time. So in this example here, I want to rethink. Instead of doing that, I want to rethink t in terms of time. In the old one, 0 frames at 2 seconds, at 60 frames a second, we'd expect to be at 60 frames and then 120 frames. And that's how we calculated it before. So, how do we do it? Well, let's just draw this out again. We still have t is 0 all the way to t is 1. Except now, instead of using the frame count to determine how far we should be, let's just pay attention to the time. So we still want to take 2 seconds to go over the whole thing. At the beginning, I'm actually going to record something. I'm going to go time, blue. I'm going to say time at start. Okay, I'm going to record that. I'm going to put it into a variable called t at 0, sure. And then at t at 1, then my time, when I get there, it should be, we can figure that out, right? It should be, well, we know we started at t0, and we know we want to take 2 seconds, so it should be t0 plus 2 seconds, right? Okay, cool. So I'm going to rethink this whole thing, and then I can even do t 0.5, and it's going to be t0 plus 1 second. Okay, so I'm going to rethink these t instead of how many frames we've gone, and instead think about how much time should have passed. And then we can invert the whole thing. At any time I'm running my program, at any time, what I do is, let's say I'm at some time t, I get the current time from the clock. And I'm going to call that t underscore c for current, t current, okay? So let's say you happen to know that we're about here, but we'll have to calculate that backwards. We get our current time. We say, well, how much time has passed? And that'll help us figure out how much we should have moved across that line. So the first thing we do is we take the current time and we subtract the time at the beginning. Now this tells us how much time has elapsed, right? So if I'm at this point here, I get my current time. However much time it is, I can subtract the start time from it, and it'll say, hey, 200 milliseconds has passed, or in this case, maybe 0.25. Maybe 0.25 has passed. Okay, something like that. Right? I should put that in pink. Don't erase everything. Okay. Now, the next step I do is I go, okay, I've figured out how much time has passed. And then what I do is I just divide it all by my total time. Or I might say I take the time elapsed over my expected time. So if I've taken 1 second and I expect the whole thing to take 2 seconds, I'm at 0.5. If I've taken a quarter second and I expect the whole things to take if I'm at a quarter second and I expect the whole thing to take 2 seconds, I'm 1/8. My t is equals 1 over 8. So it turns out that this is just my new t. Instead of t being how many steps have I gone over total steps and getting a ratio, now I go how much time has passed over expected time. So that's it. I keep track of my time at the beginning of my key point. Good. I calculate my time at any given frame. What time is it now? I figure out how much time has passed. Okay, 1 second has passed. Cool. I divide that by my expected time, and that tells me how far along I should be. And that'll give me my t. And what you'll find is you calculate that, and as the clock passes along, you move along your t. If your computer gets busy and it slows down, you skip a bunch of frames, right? But in terms of time, we'll skip here. So it'll look choppy because you couldn't draw quick enough. But when we recover, we're continued at the right spot. And then if for some reason the frame rate bullets up and we draw a lot, we're not going to get ahead. T still moves ahead at the exact right rate. Okay, so that's really cool. So in time, the motion speed is constant, even if it gets choppy. When you're faced with delays. So let's go back to our example program and let's see how we fix it. Here's the program. Now I can introduce the new things I've put in here. All I put here was t at 0, which is the beginning, not the beginning of the program, but the beginning of your keyframe, right? So we just start with some random value. And at the beginning of the program, I call the milliseconds command. Remember, there are 1,000 milliseconds in a second, okay? So excuse me, this is in 1,000th of a second. I call the milliseconds command and it tells me what the current time is. And then down here, instead of using t to be current step over total steps, what I do is instead I make my t to be how much time has lapsed and how much do I expect to lapse, right? What's my expected time? Here, I calculated lapse by just taking the current time, this time, minus my t0, just like in my notes. Okay, that's how much time has passed since I started from the beginning of the keyframe. I'm interpolating along. And then I calculate my expected time. Well, I know how many steps from the rest of my program. I want this to be 180 steps or whatever. And I divide that by my frame rate. So if it should be 120 steps, well, to keep the expected frame rate of, say, 60 frames a second, 120 steps, I divide by my frame rate. This should be 2 seconds. And I just multiply by 1,000 to put it into milliseconds. Right, into milliseconds. So I take the expected time in milliseconds, right? I divide the lapse time by it, and I get a t. The only other change I want to highlight is how do I know when I've hit the end of my interpolation? Previously, we check if we've hit over the edge of steps. Now I add an or and say, well, if t is bigger than 1, I've gone too far, too much time has passed, move on to the next keyframe. Now here, you could calculate how much more you went past by accident and add that to the next one so your time stays perfect. And there are all these other little small caveats that can make things really perfect that you'd care about in a professional system, but this is a great place to start. So now what I'm going to do, first of all, I'm going to turn off my regular frame rate. I'm going to run this to show that it works. It should still work, let's hope. Yay! So it still works by using time-based keyframes instead of frame-based time-based t calculation instead of frame-based t calculation. And now I'm going to turn on this random delay business. And what you'll notice is it'll get choppy because I'm slowing the program down, but it will stay moving at the same speed. See? It'll move across the screen, it doesn't get behind. And when it freezes, you get that break. So even with a change of frame rate or the delays or the irregular, it'll stay at the same speed. And then when the delay stops, it'll resume exactly where it left off, and we didn't lose anything. If the game reduces the frame rate, it doesn't actually go slower, it just gets choppier. All right. There we go. It's just still going the same speed, it's just choppier. Okay. No big deal. Cool. So that's time-based lerping. It's really easy to do, but it can be a bit tricky to get your head around all the moving pieces. So I recommend you go and spend some time with this example code. Thanks.